All right, I'm Brad Nelson, tinkerer on various things related to Forth, related to uh, all sorts of things, colorful pictures and so on. Um, all right, but today I'm going to talk about a thing that I've been puttering on in the background that is still not quite done, but is inching forward, and so I wanted to give a little mini update. Um, the background in this, for those that have missed the prior context, is that back in, gosh, it's now 2023. Christopher Lazinski got me in touch with some folks that sent me a pico-ice, which has both a Raspberry Pi Pico on it and a particular version of the ICE40 FPGA. It's got a bunch of flash RAM for the CPU, a bunch of flash RAM for the FPGA, and a bunch of QSPI RAM to use at runtime. And it exposes all the pins. And most importantly and interestingly to me, the CPU is able to talk to the configuration pins of the FPGA, so it can, aside from loading the FPGA from flash, you have the option to send a stream in from the CPU. So the CPU can generate have a chunk of data and stream it across to the FPGA live. And it was a pretty quick job to port micro eForth to run on this device. I think I had that maybe the month after, or even less than that. And I was pretty readily able to get a test working where I could plumb through the interface to write to the FPGA from micro eForth. So if you have a block of an appropriately generated bin file from the right kind of tools, you can stream it across and load that into the FPGA. So of course, what I immediately thought would be cool with this, and I've played around with FPGAs a little in the past, but what always kind of gets me is that you got to be in the particular development environment. You got to cultivate your particular Verilog file, and then it's sort of this game of like, well, do you are you designing a CPU? What are you trying to build with it? And oftentimes that's where I'll get stuck. So I have a number of FPGA boards over the years where I've had them and then couldn't quite find that project to do with them. And I think it relates to the tool chains being a little hard to work with. There are the cool thing with this device, of course, is that there's an open source tool chain for it. The community has reverse engineered the bitstream format, which is really cool for a device that is sort of still actively available and seems to have some evolution and is a whole family of things. And they've even built a sort of an open source Verilog toolchain for it. And they've been very open and generous in all the documentation around the format of the device. I should say, this is what the particular board in question looks like. So it's got the an ARM CPU and then the FPGA, and you're able to, and then some flash on it so that you're able to load stuff. And the bitstream format, there's tons of documentation about it. And so what I wanted to do was build the ability to synthesize directly in Forth to be able to do it on that CPU, so that the CPU generates the bitstream to load the FPGA, and it's very easy to pause the clock on the FPGA from the CPU on this device, send over a new bitstream, start the FPGA running. I believe you can even keep the state of the RAM from getting reset during that operation. So you could notionally load a set of things, change them around, pause things, change them around, reload them in sub-second. But it's been a while since 2023, and I've not given an update for some time. So what's taken so long? Mostly where I've been stuck is a better understanding of the mapping between the bits and the routing. Um, the, uh, the format is documented, but it's documented in a combination of documentation, but also a lot of code. There's a bunch of scripts, some C code. A lot of it, the approach has been from the open source effort around capturing the structure of the chips as data. And this makes sense for traditional routing methods because what you typically want to do is just treat it like a big graph problem of laying the thing out. But for dynamic synthesis, what I'm hoping to do is have enough of an understanding of the way that the configuration bits are laid out that I can have them correspond directly to a small set of fourth words that I can use. And so I need to kind of have the architecture in my head, and that's been a little bit of a struggle. Um, and the other thing that sort of stalled me out is realizing, routing is hard, right? There's a reason that all kinds of solvers get thrown at this, and so it's very easy to kind of get stuck in this mindset of like, like how will this, how often will this fail? So let me talk a little more detail. So this particular chip, and it's a member of a family, as we were talking about before the session started. It has a certain set of LUTs on it. It's got a bunch of single port and dual port RAM on the device, and it's got some DSPs on it. Basically, it's sort of a sea of these PLBs, a set of eight LUTs plus a flip flop, mixed in with some RAM resources, some DSP resources. But from my point of view, like the most interesting thing is these PLBs, just because that's kind of the minimum viable thing. It would be great to obviously take advantage of the other resources on the chip, and I certainly will need the I/O pins to be able to do anything useful. But the being able to correctly synthesize the PLBs is the main sort of minimum challenge. The way these things are laid out, they're a lookup table of 16 elements. You've got 4 inputs going in, and then there's some configuration bits that control whether or not the flip-flop is engaged or bypassed, controls where the clock for the flip-flop comes in, where the enable comes in. Some of those things, like the source of the clock and so on, are configured at the PLB level. But then at the individual LUT level, there are options to decide what happens at a reset, to flip things, to toggle the clock, to toggle the enables. And then there's also a carry in, so you can carry all the way up the chain, so you can turn it into an adder or a related structure. And there's also there's a carry in from there's some routing for the carry in from into the PLB and the carry out, so you could sort of cascade these to larger things. There is basically these purple cells here are the sort of the ones that are allocatable as PLBs. And they have between them a routing fabric that looks kind of hairy, but what it accomplishes is that there's a string of 48 wires that go horizontal, 24 wires that go across span of 5 cells, and then there's a separate, and they go both horizontally and vertically, and then there's also a connection, and it's a little easier to see in this diagram, where, actually no, I'll show that in a different diagram later. There's also a connection to let you reach into the neighbor to the right, and then there's a similar path vertically and horizontally that goes 12, or actually 13 if you go from, depends on how you want to count it from end to end, where you're sliding over and getting sort of 2 bits each time. So there's a decent amount of routing. And then let me talk a little bit about, there's this lovely viewer, which I don't have open here. Oops. Okay, there we go. Let me actually load. So this particular simulator supports a number of different samples in the family. It's cool that it's on the web. Whoops, here's one that's for the particular variant on the pico-ice. There's an option to show all the spans and all the net numbers, and then as you zoom in, as you zoom in, and let me actually zoom in here to one that's live. It even shows shows a bit of a simulation of these, and you can get a good look at the routing fabric. You can see some of the connections here and their state, and this gives you some idea of the challenges that you need to both figure out how you're going to map to these and route. So, okay, let me go back to the deck. So the format is actually, in one sense, very simple. There's it's basically just a stream of configuration bits that are landing in sort of in each block, and it does have a weird behavior on the 4 quadrants of the chip. So as you stream in the bits, you're actually filling in each quadrant in kind of a mirror reflected order, and so that has to be taken into account as you're feeding things in. One tantalizing thing that I haven't had a chance to confirm is that it appears from the format that you might be able to update only one of these quadrants and then try to reset things. So I'm a little curious about whether that sort of works in practice or not, or if some mechanism in the device will cry foul if you feed it only a quadrant. But when you feed in each of these, you have to sort of first indicate which quadrant you want to sort of start things at, and then you stream the bits in, and then you send a checksum. So some interesting possibilities there in terms of maybe being able to only reconfigure a subset of the chip. So that part of it is a little hairy, but is not the issue. This is the layout of the bits for one logic tile, and I've spent an amazing amount of time staring at this and the underlying data behind it. For a little while, I was doing this by hand by looking at the data in some of these databases and then trying to understand the correspondence with each bit position in the bit stream. At some point, and I got pretty far in terms of, you'll notice here that in the red, these bits here are the 16 bits for the lookup table for each of the eight LUTs inside of each of the rows. So they're, the bits are correspond to each individual. Each 2 rows here corresponds to one LUT. And it actually is kind of the overall ordering. The way to think of it is it's going from input to output. So there's a mapping from a variety of different options for local input into a local routing fabric, and then from there you select one of those local values to go into the input for each of the LUTs. So you're picking each of these 4 little boxed regions is one of the 4 LUT inputs, and then you're choosing that out of a sea of 32 local routing surfaces that are where you're only getting a choice of 16. There's 5 bits here for each of the inputs, but the interesting thing is that it's not exhaustive, because one of them is in an enable, and then there's a selection of 16, and there's a kind of a complicated pattern, which I'll talk a little bit about in the others. But anyways, at some point I realized I'm sitting here trying to analyze a bunch of things with a fine-tooth comb on sheets of paper. So I pivoted to just doing some code to analyze the data that's there. So the iStorm folks have for each of the different ones that they've sort of figured out the format for, a database file that contains a bunch of the information about the structure. It's broken into various sections with a prefix with a dot, and then an ID number, and then a series of rows. And so, for example, all of the interconnected pieces of wire have different names when they're in different cells. And so a net will have a number associated with it, and then this is an X and a Y coordinate within the different cells in the FPGA, and in each cell it will have a different name. So this is one of those 5-element. They call them span 4 because they're meant to let you reach 4 elements over, but they touch five cells. And so depending on which cell you're in, this particular connector has a different name because it's sort of cascading through that winding path that you saw in the earlier picture. And then there are these routing and buffer sections, and these correspond, if you go back to this diagram, to the the yellow here is the routing, and these have a particularly hairy arrangement where the 3 bits that control the routing are sometimes in a row and sometimes one up, down, kind of crossed on each other. And then there's these buffers which are sitting in the selection for the input to the LUT and the input to the local network. And for the way these are structured, you get the position of the routing in X and Y. You get the network name of where the output will go, and then it specifies in terms of the position in the configuration of that tile's logic tile which bits, and it has this odd convention of the B just means it's a bit, and 6 is the row number, and then 11 and 13 and so on are the column number. And so for each of these 3 bits, there's a table of which wire ID will get routed in. So it's a big hairy mess, right, to interpret these by hand, which I did far longer than I probably ought to. It's the same story for the buffer. Here you've got 5 bits as input and then a table of 5. And you'll notice for all of these, when everything is set to 0, then nothing is connected. So you've got it just left to float. And all of the bit patterns that actually route something or that hook up one of these buffers have at least one 1 in them. And if you look carefully, you'll notice that for the buffers, there's always one column that is always on, and that's actually the enable for that buffer. For the routing, it does not seem to have that property. But for the buffers, there's always a separate enable that's always on in every one of these. And then there's this actually just a single entry a single entry for the whole thing that describes the format of that logic tile, which is actually this convoluted picture, if you can believe it, corresponds to this diagram. So anyways, I wrote a visualizer to try to represent this in a form that I could make more sense of. And so what I did is actually generated some HTML. Originally, I had in mind of printing this out. It's pretty big, and I'm not sure it fully captures things. Let me zoom out a little bit. So this is, and actually, I don't know if I can even zoom out far enough that you can fully see it, but this corresponds to that same diagram. So this same diagram is splayed out in a little bit more detail here, and you got to pan around still to see it. So you've got the bits on the left, and I've color coded it at random just so you can distinguish different things. The blue here are the bits that make up the LUTs, as well as there's a set of 4 configuration bits. I'm going to zoom in a second, but just wanted to kind of get the visual lay of the land. So there's the routing on the left, the buffering for the local network, and then the buffering for the inputs. And then there's actually a little bit of buffering for the routing where the output goes, and we'll talk about that in a second. So let me zoom back in here. And so now zoomed in, let's look at kind of one row going across. So you'll see here that there's this things that are in the same color are actually connected. You know, I didn't have a great way to represent this visually, but you'll see like this blue element here, this one, and this one all correspond to the same. These 3 bits are choosing the element in this table to assign which of these items are connected. So here you're having the option to connect one of those horizontal spans of 4 to one of the vertical spans. And so this is giving you an opportunity to route across the chip. And then as we, and I should mention there's a couple of other random things in here. There's a bit that controls whether you negate the clock for that row. Actually, sorry, it's for the whole PLB. There's some options around routing some global fabric in the thing, which I'm not going to delve into here. And then as we pan across, now you get into, and actually, sorry, there's some more routing. Okay, and now we get into around 14 here. See this little block of 5 kind of clipped together like so. Each of these is choosing what will get routed into this local grid, and there's each of these I believe there's 32 of these. I think it's from 0 to 4, and 0 to 3, and then 0 to 7 on the second element. And so you're choosing amongst a variety of different options. The neighbors around you, these spans that reach across 4. So there's quite a few options, but it's not exhaustive. There's roughly, I'd say, half coverage of the various things that come in, and that's only for the one kind of row. And so you're choosing for each of these going down the thing out of 16 options, because in all of these, notice that there's an enable. I've marked the enable bit. So if the enable bit is not on, then you're not even routing anything into there. And you're choosing these for all 32 of these inputs. And then if we scroll over a little bit further, let's see. And sorry, there's 2 banks of these to get to 32. And then the next 2 sets of these control what gets fed into one individual LUT. So you're choosing. So now once you're actually feeding the LUT, you have to choose out of these local grid one element to go in for each of the 4 inputs going into a given LUT. And I mentioned there's 32 of these local grid elements. You're only given a choice of 16 of them in each of these. So you don't quite have exhaustive ability to map everything everywhere, but you got sort of one bit less than it. I don't know why, given that they had 1 extra bit to blow on this enable, they didn't do more. I'm assuming that there's some reason that makes more sense if you see how they're implemented in silicon. And so that's how you choose for all 8 of the items, all 8 of the LUTs in the PLB, what feeds them. So you've got sort of 2 layers to choose how you route them down. So there's many paths to take any given input that you might want to get from your neighbors or from these spans of 4 or spans of 12 into the local group, and then from the local group into the input. And then you have 16 bits of the lookup table. This is, I've labeled them here as in terms of what bit pattern for input this specifies what output you get. So you got a table of the 16 different bit patterns, and then choosing which of these will go to the output. And then you have 4 configuration bits per LUT, where you choose whether or not you swap the input 0 with the carry rather than the input coming in from the side. You swap whether you enable the D flip-flop that's sitting behind the LUT, and then you toggle whether your reset state for the flip-flop is active or not. And then I'm forgetting off the top of my head here what this async set reset is. And then this is on the after you get the output for each of these, for this LUT output, you have the option to then feed that into many of the different exit points. And there's a pattern here where you've got a subset of the outputs that you're able to route each of these to. So you're not able, again, to send them everywhere, but you have a number of choices per row. So that's the structure that I'm trying to map to. So let me jump ahead here. So using that tool, I was able to figure out that, for example, per bit, you're able to map the output to every. There's this pattern of 3 positions per row in the PLB that you can map a bit to in terms of where it drops in the horizontal spans. And then similarly for the vertical spans, there's 3 options as to where to drop things. And then there's also a second option to feed your right-hand neighbor the interleaved versions of these. So it's these same positions shifted over by 1 in the neighbor, which is a little complicated, but and then for the outputs, there's this very narrow set of selections in terms of for each of the PLB bits, choosing where to drop it in each of the horizontal spans. So it's very structured, but it's a little it's combinatorics to it. So I think I have enough understanding that I would be able to use those now if done carefully, but I haven't looked at I/O yet. I've been assuming to bootstrap that I will just synthesize using the OSIS tools, some set of I/O pins that I will just use as a harness to start. And there's options for phase lock loops and so on in there. The globals are routed in a complicated arrangement. There's this weird structure where certain particular extra bits in a couple of the logic tiles choose how the globals get routed in some complicated scheme that I don't yet understand. So now I'm going to pivot to something else. I wanted to give folks a sense of like where I'm trying to go with the synthesis here. So I've got a simulation that models how I'll synthesize once I have all the encoding issues worked out. Initially, this implementation is just very memory wasteful. What I need to change to, and I'll talk about this briefly at the end, is to use the FPGA bit space instead of allocating structures in memory. So the little DSL that I want in Forth needs a way to talk about a couple of things. It needs to talk about multiple wires at once. I have an abstraction I call a bus for this, where you're able to just sort of glue several wires together into a bus. It needs to be able to support allocating registers. It needs to be able to support doing multi-bit logic and arithmetic on those values, and then eventually routing them into a register. And then it also needs to be able to support the clocks and the enables on these registers and flip-flops. So let me just go through the simulator's implementation. What I'm able to use as a convention is that for the simulator, I can just use a regular variable as a data input, like a pin. So I have some for 0 and 1s, and then I keep 2 linked lists of all the LUTs and all the flip-flops, which I currently allocate separately in the simulator. And then I keep a variable that is meant to be updated by the person using this for synthesis to specify for the next set of registers or flip-flops to allocate where they should have their clock come from and where they should have their enable from, because these need to happen in chunks. And I just initially set their clocks to not be connected to anything, just to 0, and to set them to always enabled. And so I'm using the structure library that I have built into Micro eForth to manage these. For each LUT, this is obviously very wasteful to allocate, but I'm currently keeping track of a cell for the current value of the 1 bit, a chain to the next LUT in the chain linked list chain, and then the address of the inputs for each of the 4 inputs, where they come from, and then a single cell that has the 16 bits that specify the lookup table. And then for flip-flops, I have a similar structure. I always put the value first because that way I can treat the beginning of each structure as an input. And then I have the chain for the next one, the input, and then whatever the enable and the clock was set for that flip-flop. And then I have to keep track of the old clock value, what the last clock value was, in order to be able to detect edge transitions, because the built-in plumbing on these flip-flops assumes that you will do an update on an edge. Right now, I just assume a low to high is the only option. Although on the actual FPGA, you have the option per bit to toggle the meaning of the clock. So using this framing, defining a LUT4 is pretty straightforward. I take in the 4 inputs off the stack, as well as the lookup table, and then I output a single wire that describes the output. And all I'm doing to accomplish that is keeping track of where I'm at in the dictionary. I store a 0 for the initial value of the output of the LUT. I connect in the chain to the prior LUT, hook in the 4 inputs, store the input table, and then update the linked list, and then keep a duped copy of the output so that you can hook that up to other things. When I want to simulate the LUT, it's pretty straightforward. I have a word here, LUT vals, that goes through and extracts each of the bits from the current input value of each of the 4 inputs, combining them by ANDing them with a mask, and then ORing them all together. So I get a value from 0 to 15 for the current input value. So then when I want to tick one individual LUT, I just have to take a look at its lookup table. I get the LUT value. I do a right shift by the number of the 0 to 15 value, and then AND off whichever bit that is, and check to see if it's non-zero. And based on that, I update the value. So I'm just doing that lookup table for the one LUT. And then to tick all of the LUTs, I just have to start with the set of LUTs, loop while I don't hit a 0, and then tick each LUT, and then go to the next LUT. So that's how I tick the LUTs. I do something fairly similar for the flip-flops, initializing them. And then it's a little trickier because I have to look at the state of the clock versus for that particular LUT versus the old state of the clock. I update the state of the clock, the old state at the end, and then if the appropriate things are enabled, then I update things. And same kind of story to loop through all the flip-flops. So simulation just becomes ticking all the LUTs, then ticking all the flip-flops. And then when I want to do some number of ticks, I just have a simple word that does multiple ticks. And in case it's not obvious, for combinational logic, you have to do several ticks to allow things to cascade through the simulation. Using this LUT, these LUTs, I can then build things like XORs by just putting in the appropriate value in the lookup table. I put in 2 of the inputs as just zeros. I probably don't actually have to have all of these specified this way. I could have probably just put the bottommost bits, but I just did it that way. For XOR and invert, with invert, I'm putting in zeros for 3 of the values. Very wasteful, right? You're blowing a whole LUT4 for a 2-input thing. But in any event, then I can use those to build, for example, a half adder and a full adder out of them. And then here's where I'm implementing the bus logic. So buses are just this idea of combining multiple wires. And the way to think of them is just they're a series of pairs where you're attaching one more wire to the bus as you go. So the word bus sort of packs in one more wire. The word unbus unpacks one wire. And then I use the convention of a 0 for the bus to mark the end of the bus. I have a word nbus that lets me take n wires off the stack and combine them into a bus. And then I have the word n unbus, which just loops through the bus and drops all of the elements onto the stack until I hit a 0. So I can sort of get the wires back out again. I have this word to print a bus where I'll go through and unpack each element on the bus and print it, its current, the value currently on that wire. And then I also have a word to store into each of the elements in a bus, putting one thing in each bit position. Using that bus abstraction, I can then build high-level words that operate, and here I collide with the built-in words. These are in the implementation, often a separate vocabulary. These collide with the normal fourth words for invert and or and so on. But what they do is they recursively loop through and support allowing you to do an invert on a bus that has multiple wires. Same thing with two buses that have multiple wires for ANDing. I don't actually do error checking here if bad things will happen if the number of wires in the buses don't match. And so you get two buses in and a bus out. Same thing with OR, same thing with XOR. And then I can also build a carry, an add with carry that takes in two buses plus a single wire for a carry in, and then outputs a bus with one extra element for the carry. And then to simplify things, building on that word, I feed in a 0 for the carry in to give me just a regular plus. So this will take two buses with n bits each, and you'll get out a bus with n+1 bits. A register is pretty straightforward using this framing. You can specify the number of bits you want in the register, and then it will just allocate a set of flip-flops, assembling their outputs into a bus. Their output is also a way that you can find your way back to feed the input. For the flip-flops, I don't pre-assign what the input to the flip-flop is. That's something that is initially set to feed from 0, but the idea is that you do all your combinational logic, feed it over into a flip-flop or into a register, and then at the end hook it up. So you start with the registers, do a bunch of combinational logic, loop back around, and then feed into the registers. Reg bang hooks a bus of multiple values into a bus of multiple flip-flops. And at this point, I'm going to switch to a demo. So I'm gonna, I can find my way over, share a different screen. Okay, so I've got that simulation code that I just showed you in this file. And over here, I've got a test, and this give you a sense of what synthesis in this world would look like. So this is the sort of the moral equivalent of the what you would do in lieu of Verilog in this world of being able to do on-device stuff. So right now I don't have an abstraction for an external pin, so I'm just using a variable to declare a clock as its own pin. I set that as the clock that will be the default clock to use for any flip-flops declared after this point until the next time that changes. I allocate an 8-bit register and put the bus for it into V1. I then change disable the enable for any of the upcoming flip-flops to be 0 so that they won't be clocked by default. And then I allocate a second register V2. From this register, these two registers I'm able to generate their sum, and I put the reference to that bus into sum. Same thing with and or and XOR. And then I take the sum bus and I strip off one of the bits so that I can get, instead of having a 9-bit, sum is 9 bits, but I only want the lower 8 bits. So this is a convoluted way of me pulling out the 8 bits. Probably something that could use a convenience word around it. And then I feed into, I feed that 8 bits of the sum as the input to the register. So on a clock, V1, so V1 and V2 are getting added and XORed that are fed to these different places. And then I'm also feeding the sum of them as an input to register 1 that will get clocked in on a low to high. And then for V1, I just go ahead and set that register to the value 1, and because I disabled its enable pin, it's just stuck there. So you've got 2 registers, one of them set to 1, one of them clocking in the input of the sum of the 2 of them. I have this word show that prints out their current values. I have a word cycle that will cycle things forward and then show the value of things. And then I have this word C, which actually alters the clock. So it sets the clock to 0, does 100 ticks, sets the clock to 1, does 100 ticks, and then shows the result. So let's give this a whirl. So first I'm just going to do a regular cycle, and notice that everything is just showing me so you got V1 and V2. The V1 is set to set to 0. V2 is set to 1, and their sum is 1, and their AND is all zeros. And to be clear, they're showing the bits in reverse order. So the least significant bit is on the left. And then their OR is 1, their XOR is 1, and so on. And if I were to, for example, change V1 to be, let's say, 3, oops, what's the bug there? 3, why does that give me an error? That's strange. Oops. 3, V1. Demo fail, of course. That's weird. All right, I'm going to ignore that. Not sure what's going on there. But anyways, now let's try, so we've got things in this initial state. Let's actually do C, which will actually cycle the clock. And now what happens is that the sum incremented, because now V2 is still 1, but V1 is now also 1 because of the sum of those. And if we keep cycling, you see that the sum keeps incrementing. Oops. And so it is acting as a counter on each clock cycle, ticking things up. And so the idea is that this approach will allow for composition, so that you'll be able to build more complex modules out of registers and out of various logic operations, combinational logic, and that will allow you to do your synthesis and operation. Let me switch back to so one issue with the synthesis is that it doesn't, right now it's allocating a bunch of things in RAM, which is not directly helpful for synthesis, but also is very wasteful. So what my plan is to do next, now that I've got a pretty good handle on the format, is to switch to, instead of passing around the addresses of these structures allocated in memory, to pass around addresses in the space of the FPGA. So referring to the bit position, the X and the Y coordinate in the FPGA, and then to use the bitstream layout to store the truth table information, to store information about the 2-layer route. And then for simulation, I'll have to have a couple extra bits that I store somewhere else, 1 bit for each LUT and for each flip-flop to keep track of the current state, and then 1 bit to keep track of the enable. Sorry, I said the enable state, but I meant the clock state. And then I'll probably need to mix into there some Sentinel values to refer to things like no connection and the globals. Carry in this framing is going to be a little weird. In a normal synthesis tool, it will sort of figure out that there's this option that these LUTs have been laid out in a way that you can do a carry kind of nicely because they're built to be adders. My current thinking is that I would handle this as a special case. So have a word that allocates a register that's sort of a special adder style register. One other kind of issue is that because I'm first allocating registers, doing a bunch of combinational logic, and then wrapping them back around to feed the input to the register, by the time that you've allocated that last LUT to do whatever combinational logic, it might not be in the same cell with the flip-flop. And so there's a little bit of a problem. How do you know that you're just about to wrap around back to a register or flip-flop? And so my initial thinking is I'll probably just punt on that and waste one, basically have flip-flops that are actually being used sort of have a no-op LUT in them. But there may be some smart scheme where I can figure out, okay, I'm about to feed this into a flip-flop. One issue with that, though, is that if you feed it into a flip-flop and then you want to use it somewhere else, now you need a second copy of it. So there's a little bit of a wrinkle there. I am a little bit worried, though, about that routing fabric still, because the issue is it is not exhaustive. It has the property that as you connect something up, you've marked everything with a series of ones. You can tell from the control RAM format what you've allocated, but what it doesn't help you do is figure out, well, if you sort of tried a path and it didn't work, now what? And so you have to. There's a little challenge there. So I think my next step is I need to just bite the bullet. I've got the format basically figured out. I need to just go ahead and do this allocation of the paths greedily. Sometimes it will fail. I've had a few thoughts as to how to deal with that. The simplest one is just allow the user some control over allocation, so that if you're trying to add a series of things and then you hit a case where it, for whatever reason, isn't able to allocate things, let the user put in a hint so that you say, no, actually, I'm going to put this LUT over here because that will free up more routing to be able to get to it. I'll bootstrap with known good pins, and then I still have an implement. I've started a couple times and not finished on the. There's a fairly simple checksum algorithm that you have to prep for these bit streams. That as you output bytes, you just update a very simple checksum, and that needs to happen in order to write things, and then it will be lots of debugging on the board. So that's the end of my talk. Are there questions? I'm going to look at the chat now.
Well, Brad, I'm watching this in a sense. It's why I'm here, because to connect the array language evolved from APL to the arrays in Silicon is, very, again, it's why I'm not over there with an APL crowd. I'm over here with the extension to the hardware. So, fantastic. I really wonder what the languages are that you're going and doing all this array, logic with.
So for the analysis, for generating that, this is where I confess, for generating that visualization, I did end up using Python because it ended up being something where I had a bunch of dictionaries of things, and honestly, I think some of the tooling from the Yosis folks was doing similar. So it was a, they built their world in a way that made it hard to do something else. But yeah, it's also a little bit of a strange choice, that they built their, given that all of these PLBs are essentially identical from what I can tell. It's peculiar that they've gone to great lengths to basically store in the database for each of these this identical layout, assigning them kind of random numbers. So yeah, it's an odd situation. I get where they're coming from though, because they're trying to make it generic. They want to make it into a generic graph problem so that they don't they can separate out the figure out what the structure of the chip is separate from the problem of synthesizing to it. But for my case, I want to take advantage of that structure. If for example every single PLB in the thing had been a completely different layout, I would have looked at it and thought, no, this isn't. This is this will be no fun because you'll have to have some fidgety set of rules. But it looks like each of the PLBs is basically the same cell copied over and over again.
Well, I got a couple of notes I'll go through on my time later, but um, the regularity. Well, I mean, you look at what my logo is, which I did in APL in 1979 to sort of show the value of artificially aided thought, and I mean it's a cube. I've only had a couple of people go and say instantly how many dimensions it is. But I mean, it's and the hard part was drawing it with a single continuous line. So you
I,
know, when I see when I see these sets of lines that are going like this, and then that little pair, each of those little pairs,
yeah.
it's like, whoa, this is.
Yeah, it's hairy. I noticed in the chat, Ken, you'd asked the question. Yeah, am I working to a solution that does not require Verilog of VHDL? Exactly. That's the goal, is to be able to directly generate the bit format, so that I'm not reliant on those tools. But then, of course, I will be very reliant on the architecture of the ICEs. Ken?
Hey, Brad. Yeah, thanks for a great presentation. Um, I'm just still trying to assimilate this because historically VHDL was um, a spin-off of Ada. It came out of the Defense Department. Very long, um, hung closely to C syntax. And Brad, I think what you're doing is you are creating something that fourthers can use to uh, program programmable logic um, using a fourth syntax. So think about a good name for it and register it as soon as you can. But no, seriously, you've done excellent work um, understanding how the LUTs are programmed from basically a bit file from a little flash or whatever. And it would be so cool if, okay, it's an up 5K that you're dealing with at the moment. Yeah. It'd be so cool that if um, you came out with a fourth toolkit that, I could say, yeah, I want a full adder, or I want a 16-bit program counter, or I want a 16-bit universal shift register. And, you know, we could pick those fourth words and it would twiggle the bits for us. Yeah.
Yeah.
So, um, Brad, I've really enjoyed your presentation, and uh, I I hope that you manage to make even more progress. Thank you. If anybody else has a quick question, and by quick I mean quick, now's the time. Otherwise, we need to move on.
Kevin, can you hear me?
I can hear you. You're up.
Okay. All
Introduce
right.
yourself and get started.
All right. So I'll just trying to share my screen now. Oops. All right. Can you hear me?
I can hear you.
Yeah, I have to restart my Zoom for some
I hate when
reason.
that happens. In the meantime, I'm wondering if Brad is going to be able to export designs to OCAD and produce masks for full custom chips.
I don't know. We'll see. Oh, I just realized I forgot to show a scary. Before I made my synthesis tool, I tried, or sorry, before I made my visualization tool, I tried to throw things into GraphViz. So I got this scary picture of the same layout represented as a giant graph, which I'll throw in the chat for folks to look at. But let's just say it's not understandable at all.
Hey Brad, um, I know there was